So, last time I stopped at the finesse in case of transmission through a Fabry Perot. So, transmission through a Fabry Perot, we did it by deriving the factors that affect the transmission of a multi-beam interference. Okay. And finally, we came to the conclusion, or we came to a final formula which looks like this: I upon I0 is equal to I upon A sine squared delta by 2, where delta is of course the phase between all those rays that are coming out, and it is an infinite number of rays that we had assumed, and A is called the finesse or the coefficient of finesse, which depends completely on the reflectivity of the two surfaces of the Fabry Perot. Okay. And we had seen that this is the graph that we can plot, where delta is the phase difference, path difference, phase difference, and T is the transmission, which is I by I0, and you will get the maximum transmission from that Fabry Perot. Now, that Fabry Perot is like an instrument. So, you will I will just draw it as a block like this, Fabry Perot. So, now you have an input light. Okay. So, this will be the output, input. Okay. So, we are looking at it as an instrument, the Fabry Perot. So, I have an input beam, I have an output beam. So, what I am trying to show here is the output beam 0 or is the output beam to the maximum, which is 1? Is the transmission of the Fabry Perot 1, or is the transmission 0, or is the transmission half? Okay. So, this was the consequence of the interference between all those multi-beam wave. Okay. And as a result of that, we are getting some output. And what we find is that the output depends on the reflectivity of the inner surfaces of the Fabry Perot, which is given by the finesse. So, depending on the finesse, my transmission will be 0, half, 1 or anything in between. I would want it to be 0 or I would want it to be 1, because that gives the best interference pattern. But then again, I am not interested in say 1 here if the image is so blurred, like this purple diagram. I will be interested in this red kind of interference pattern. That means I get a maximum transmission and I get a minimum transmission, which are well separated out. You can distinguish the maximum and the minimum very well, and that is all because of the coefficient of finesse. In case of the purple curve, you cannot distinguish the maximum and the minimum very well, because see, the minimum is not 0 and the maximum may be 1, but the minimum is not 0. So, that contrast is not that good, or the visibility is not that good. See, here the factor visibility comes into the picture. The maximum and the minimum, the difference should be well contrasted. Okay. So, in case of this purple curve, it is not that well contrasted. In place of the green curve, in case of the green curve, the contrast between the maximum and the minimum is not so bad, and the contrast is best in this red curve. Though this transmission may not be 1, but between this, the top transmission and the bottom, the contrast is very good. So, the visibility of this curve is much better than the visibility of this curve. Remember, the visibility depended on the maximum intensity and the minimum intensity. Okay. So now see this, and this depends on many other factors. Of course, it depends on the delta and other factors, but along with that, it depends on this finesse, high finesse and low finesse. And high finesse and low finesse is brought about just by the reflectivity of the inner surface of the Fabry Perot. See, it sounds a bit strange. I just have these two plates, and I may get an output light here, and under certain conditions that the input beam with a certain wavelength, I may not get anything at the end. So you may have shut off the light completely. Okay. So it is the same wavelength which is coming out here. But under certain conditions of the reflectivity, I get 0 output or 1 output or maximum output. It's really an amazing instrument. Okay. So I have control on that instrument by just making the reflective surface to whatever I want. So I make the good reflective surface, and I can change this finesse. Okay. So this is used in many cases. Let me just see what are the modes in a Fabry Perot cavity. Okay. So here I'll just, yeah. So the modes in a Fabry Perot cavity, that means I have, remember I had spoken about modes in case of laser resonator. So the laser resonator is actually a large Fabry Perot itself. See, a laser resonator consists of mirror on this side, and then you have the light traveling between these two. A Fabry Perot also, as I have described, is exactly that. You have the light reflecting up and down. You have two reflecting surface, and you have either some output or 0 output, maximum output or 0. So there are certain kind of modes which are developing between these two surfaces of the Fabry Perot. That is what I want to describe in this. I will go back to the similar formula, this formula before. Phase difference between neighboring rays, we have seen, is equal to k delta 4 pi by lambda d cos theta. The total transmission comes about when delta is equal to 2 pi n. We have seen that. Okay, when the phase is 2 pi by n, n is the integer, 2 pi by n is equal to 4 pi by lambda d cos theta. That also we have seen. So if you combine these equation, n delta is equal to 2d cos theta. Okay. So this is from just I am juggling some bit of jugglery from whatever in the previous slides. Okay. I start off with the phase difference between neighboring rays, and I come to this. Okay. So n lambda is equal to 2d cos theta. Suppose I make this theta 0, that means the beam is incident normally on the surface of the Fabry Perot. Okay. So instead of it being at an angle like this, it is coming in normally. Fabry Perot here, and I am getting a normal incidence. Okay, so that theta part I can eliminate then. Okay, so theta is equal to 0. So n lambda is equal to 2d here. Theta is 0 means cos theta is 1. n lambda is equal to 2d. Lambda is equal to c by nu, you know that. C is the velocity of light and nu is the frequency. So, when n is 1, then c by nu 1 is equal to 2d, nu 2 minus nu 1 is equal to c by 2d. So, it is when n is equal to 1, lambda is equal to 2d or c by nu 1 is equal to 2d. Okay. And when n is equal to 2, 2 lambda is equal to 2d. So, lambda equal to d. So, c by nu 2 is equal to d. Okay, so I have just made one extra 2d has come in here. Nu 1 is equal to c by 2d. Nu 2 is equal to c by d. Okay. So, one extra, one of them have to be cancelled anyway. So, then I take the difference between these two, nu 2 minus nu 1 becomes c upon 2d. Okay. This formula should be very familiar to you. Remember, we were, why did I bring in the frequency here from the wavelength? Because remember, that time we were speaking about the separation between the two frequencies, or separation between the modes, and modes are frequencies. That time I had just given you the separation between the frequencies, or separation between the modes is given by c by 2d. D is the distance between the two mirrors or the cavity length. So, but I hadn't derived anything. So, the genesis of c by 2d, this formula, is from here, is from this Fabry-Perot. Okay. So, that is what I mean by your the modes in the Fabry-Perot, modes of the Fabry-Perot cavity are given by this, and the mode separation is given by this. Okay. And a resonator, a laser resonator is a large Fabry-Perot with two mirrors or on either end, and there is a distance between them. I had at that time I had spoken about c by 2l. I had L was the value, here it is d. Basically, it is the distance between the two mirrors. So, between a Fabry-Perot which has two mirrors closely spaced together, very close to each other, there is very little difference between that and a resonator mode. Okay. So, the difference in the modes, now even in a Fabry-Perot, here there are certain modes which are developing, and the spacing between the modes are fixed by c upon 2d. Okay. And by and remember, by changing, that means if we change the distance between these modes, or if we change the distance between the two mirrors, that means L. Okay. I am changing the L, or I am changing the D. I am bringing the mirrors close by or far. Suppose I am bringing it, I am bringing it closer and closer. Okay. That means the mode separation is becoming larger and larger. Okay. So, in case of a Fabry-Perot, I am bringing these two mirrors closer and closer. As I bring them closer and closer, the mode separation becomes larger and larger. That means only only one mode can be found in this. One mode means only one frequency. One frequency means only one wavelength. Okay. So with the use of a Fabry Perot, I can even tune, specifically tune the laser or anything. Basically, it works like a interference filter. See, it basically works like an interference filter. Under certain conditions, the Fabry Perot interferometer transmits a light wave of a certain wavelength through it without any attenuation. The waves whose wavelength differ only slightly from lambda are completely attenuated during their passage. The Fabry Perot acts as a narrow band filter. That's comprehensive, no, to you. That means, so many, you look at the picture in this way. As we did all the derivation, we spoke about just one wavelength, lambda. We stuck to lambda. We did not say lambda 1, lambda 2, lambda 3. We started off with just one lambda. Okay. But the interference pattern that has taken place in this Fabry Perot, it's true for any lambda. So suppose there were lambda 1, lambda 2 and lambda 3. Each of them would have had its own interference pattern. Some part of it may have been, some part of it may overlap, some part of it may be covered up. So the blurring of the interference pattern occurs. So the blurring of the interference pattern will not happen, or the visibility will be very high if there is only one lambda. But then that's not always the case. Absolute monochromaticity is never attained, which you know already after all these lectures that we have gone through. They all have a spectrum. There is a delta lambda. So there is a lambda 1, lambda 2, lambda 3. So out of all these lambda, how do I select only one? Just by using a Fabry Perot, which acts like a narrow band filter. Okay. So I just try to bring these two mirrors closer and closer and closer together, very close to each other. Okay. And I select just one mode. So though there are other wavelengths within it, I am able to make it work like a narrow band filter. That is the importance of a Fabry Perot. And this C by 2D or C by 2L, the genesis of this formula is a Fabry Perot. And I am comparing the Fabry Perot to a laser resonator itself. Now in case of the laser resonator, the two mirrors are far apart, much more, there is a bigger distance. So number of modes that can laze are much more. So I could actually have a laser resonator. Say I am showing it with curved mirrors, the laser resonator, because that's how they are stable. And the lasing action is taking place, and it has a bandwidth to the beam that is here. Okay, the beam that is here, it has a bandwidth, say like this. Okay, so there is a certain delta lambda attached to it. So it's not just one lambda 1, lambda 2, lambda 3, and few others are there. But I want, for spectroscopic purposes or for some purpose, I want only one lambda, just that central one. I don't want the ones in the wings at all. Okay. So how do I do it? How do I filter it? Like previously I had said, that time I had just mentioned a Fabry Perot, I did not describe to you a Fabry Perot. I had said one way of doing it is by coating these mirrors so that only one wavelength is reflected back. Okay. Or you could place a Fabry Perot here, a small Fabry Perot here. So as it passes through this Fabry Perot, the Fabry Perot acts like a narrow band filter. Narrow band because it allows only that one narrow lambda 1. It does not allow the next lambda 2 at all. So you place it inside the resonator, and finally what you get out of the resonator will be just one lambda 1. Okay, that was the use of the Fabry Perot. Though I had, there are many other ways of tuning, which I have said before, like grating, etc. But this is also another way of selecting just one wavelength. Okay. So this whole principle, actually it is interference in thin films is also followed by the same principle of multiple beam interference by amplitude division. Okay. Thin films is the same. The ray incident on the film at the same angle are divided into two rays which become parallel after reflecting from the surface of the film. A path difference appears between the rays reflected at different surfaces of the film and hence can interfere with each other. So basically the principle is just the same. This is, say, a thin film. So I have a ray which will go here and it will come out and it will go here. Okay, so there will be many. This is one surface and this is another surface of the film. It is a very thin film. So again the same principle of two rays interfering with each other from one surface and the other. In a Fabry Perot also you had the same thing. One ray which is getting reflected and then part of it which is transmitted. These two surfaces are like the two mirrors of the Fabry Perot. So the same principle is used and you get an interference from thin films. And a good example is, oil spill on you've seen oil spill on water. It gives those fantastic colors and all. It's all because of the interference between the layers of that of water and the oil. And the oil which forms a very thin film. Different surfaces of the oil, the lower surface and the upper surface, you will get an interference pattern and that is where you get the colors. Colors obviously come from those wavelengths depending on the thickness of the film or thinness of the film. Okay. So I think there should be a little bit more clarity. So I would like to choose a Fabry Perot which has a good finesse. That means I would like to choose a Fabry Perot which has its surfaces polished very well, okay, high polished surface. So you will get a good finesse, and if you have a good finesse, then you get a good contrast, high contrast between the top part and the lower part. And good contrast means best visibility. And another way of looking at it is getting only one wavelength out of the Fabry Perot, not allowing the other waves to, making it work like a filter. Okay. So going through this derivation gave us an idea of what a Fabry Perot, how a Fabry Perot works, which is a fine example of multiple beam interference through amplitude division. Okay. And I think I should stop here, but before I stop, I'll just give you a hint of what I'm going to do in my next few lectures, which will be on holography. And why do I choose holography? Because since you have understood interference pattern in so much detail, and you have understood how phase difference, path difference works to an advantage to get good interference pattern. Holography is actually based on this interference pattern. So, at this stage I think you will be able to understand holography very well, because it is based on how to get different kinds of interference pattern and how to read those interference pattern. Okay. So, this is the right time to introduce to you holography, which I will do in my next few lectures.